And finally, this is going to be a long video, I'm sorry. The last example, let's grab an out of that. Minus 1 to the n factorial to the power of n to the n squared. Okay. Well, again, to remind you, this is an alternating series. You can use the alternating series test to deduce something about the convergency of this infinite series. But since in the question statement it was asking to use the root test, so let's just use the root test. Okay. So limit as n approaches infinity, nth root of the absolute value of an. Okay. Like in the other cases, let's see. When you take the absolute value of an, well, let me just write it clearly. But minus 1 to the n part is going to be gone. Okay. N factorial to the power of n to the n squared. Okay, and I take the absolute value here. Let me just put the absolute value sign right here. Okay. All right, minus 1 to the n is always 1, so I'm going to get rid of that, as I said. All right, so I'm left with the absolute value, n factorial. So now I'm going to rewrite n to the n squared, which is in fact n to the 2n, as n squared to the power of n. Okay, so I want to grab the power n so that eventually I'm going to take the nth root, so I want to get rid of that. So n factorial, n squared to the power of n. There we go. So n factorial is coming with power n squared is coming with power n. So why don't we write all in one shot that this whole expression is reduced down to the nth power of n factorial over n squared. When you take the nth root, this becomes n factorial n squared, and since this is a positive expression, I don't need to carry forward the absolute value sign, and n approaches infinity, so n is large, so top and the bottom are always positive. Well, at this moment, you can stop the video and start thinking about what this limit could be. So it's n factorial, n squared. N factorial is the product number starting from n going all the way to 1. Even if you consider this in the sense of L'Hopital's rule, so you have at the top you have n minus 1, n minus 2, all the way to 1, versus it's just n times n. Okay, so which essentially means that, well, this part, let's say this n cancels this n, and then putting these two terms together, you still have a lot of n related terms at the top, right? So even if you take care of n minus 1 and n, right, these are like terms, right, the rest would take this whole expression go to infinity. Okay. You can also see this by rewriting this as by just dividing everything by n, in other words. So this is 1 minus 1 over n, 1 minus 2 over n, right? Like, let's just do this. Let's just divide this top expression by n, and then just keep the other terms. Right, n minus 1, right? So now I have nothing left over in the bottom. And when you pass the limit, this term is fine, but the rest will take you to infinity. Okay, so for that reason, this limit is infinity, or in earlier days we were calling it doesn't exist. So that makes this function, the series, divergent. Okay, so I'm going to go back and say like this is divergent. And what are we using here? Well, we're using the fact that if the limit value is greater than 1 or infinity, the series is divergent. Okay, I think that ends the video. So we had 4 different examples. We had 3 convergent cases and 1 divergent case. So please practice more with those problems in the book. and try to have like a good grip of the application of the ratio test and the root test. All right, I'll see you in another video. Bye.